When we have a correlation, we simply have a situation where one variable increases or decreases while another variable also increases or decreases. Another way to put this is covariation. The variables vary at the same time. They covary. And a common example used to illustrate this is the relationship between ice cream sales and drowning. When ice cream sales increase, so do incidents of drowning. But does eating ice cream cause you to drown? Nope, not likely. In general, ice cream does not cause you to drown. So what is a more likely explanation? More people are going to be in the water because it's hot. And because it's hot, more people are also going to buy more ice cream. If you're in the water more often, or more people are in the water because it's hot, you're just by the fact that there's more people in the water, there are going to be more drowning incidents. So another way to put this is that although ice cream sales and drownings correlate, ice cream does not cause drowning. Correlation is simply telling you that there is a relationship, two things co-vary. But causation requires specific requirements to be able to say that one thing caused another thing. The cause led to the effect. And correlation is one of those requirements. When these elements exist is the only time researchers should use causal terms, because otherwise you are misleading your reader to think that you found a cause and effect relationship. First, you need to have a correlation between the cause and effect, meaning, as we just went over, as one changes, the other changes. You also need to have the cause come before the effect. Something can't happen, or something can't cause something else if it comes after it. Finally, to be able to say with certainty that something causes another thing, even with those first two elements, you also have to be able to rule out any other potential explanation. And this is basically the whole goal of science, the whole goal of experiments. These are exactly the elements that experiments are designed to establish. Experiments are the gold standard in being able to establish a cause and effect relationship. Think about this organizational example. We have a company, they want to, and this is a very realistic organizational psychology application of an experiment. But let's say that a company wants to implement a new training program designed to improve knowledge of ethical AI use before they roll out a new AI tool. They ask you, the organizational psychologist, to help them confirm whether the training is effective at improving knowledge of ethical AI use. Companies all over the place in many different areas are implementing AI tools. And so one of the things that IO psychologists or organizational psychologists are recommending that companies do is implement trainings like this. So this is something that you will probably see happen a lot more frequently in the near future. In this situation, what is the cause or the independent variable that we're after? The thing that we want to increase is knowledge of ethical AI use. So we want that to increase. So that is our effect, or our dependent variable. The company is deciding, whether to invest in this training program that is supposed to increase the knowledge. So the idea, what we think is going to happen, or what we were testing, is whether the training causes an increase in knowledge of ethical AI use. So in this scenario, whether or not people receive the training is the independent variable or the cause. And the effect is knowledge of ethical AI use. So first, to even just establish the first element of causation, which is that there is a correlation, we have to observe change in both the cause and the effect. In the case of our training example, people can either receive the training or not. If everyone receives the training, then our measurement of the independent variable or IV or cause will be the same for everyone or constant, which is the opposite of change. And we won't be able to determine if change in the cause is associated with change in the effect if we don't have variation or change in the cause. So we have to have some people who have received the training and others who have not received the training. In experimental terms, this is known as manipulation. This creates our measured values for the cause or training. It could be something like 1 equals received the training and 0 equals did not receive the training. To put this in research terms, the group of people who received the training would be called the experimental group or the treatment group. And the group of people who did not receive the training would be the control group. So we have change between the groups on whether or not they received the training or not. So now we can observe whether that change between getting training or not getting training is associated with a change in the effect. And the effect is a little bit simpler to observe change because there are more possibilities. For example, the knowledge test could be very similar to a test you would take in school. You would have a score from 0 to 100 based on the percentage of questions you answered correctly. The variation will come from the differences in scores across each individual who takes the test. For example, I might get a 50 and you might get a 95. The scores changed across from me to you. That would allow us to see if there is a correlation. And beyond correlation, the next requirement for causation is that the cause happens first. To make sure this is the case, we have to at least measure the cause at an earlier time point than the effect. This means that cross-sectional designs are unable to establish causation. A cross-sectional design is just where you measure all of the variables at the same point in time, and so you don't really know which came first or not. In the context of the training example, it doesn't really make sense to test their knowledge while they are in the middle of training, and it definitely doesn't make sense to only test their knowledge before the training because, they haven't received the training yet, so we can't tell whether the training will cause them to score in a certain way if they're only taking the test before the training. In our example, we would need to make sure that the training on ethical AI use is delivered before we measure the effect on employees' knowledge. But even capturing the cause before the effect is not sufficient. It's not enough. So let's say the company let employees volunteer to take part in the training on ethical AI use, and not all employees volunteered. So we have a change in the cause to allow us to check for correlation. And let's say we measured all employees on knowledge of ethical AI use after the training. So we have the cause coming before the effect. Let's even say that the group that volunteered to take the training scored higher on the test than the employees who did not. Can we say that the training improved knowledge? So if some people chose to take part in the training, and then people who didn't want to do the training didn't take the training. So there's several other potential causes that we haven't ruled out. And so it is likely that it caused it, but there are also other explanations that are at play that we need to control for. So what else could be causing the differences in knowledge in the situation? Yeah, previous experience in the situation. So maybe they are just more familiar with AI use and therefore more interested in getting more training. And so their previous experience is going to help them probably score better on the test, even if they wouldn't have taken the training. So people who volunteer could have some previous experience, some different interest in the training that could be what is actually causing them to score better on the knowledge test. So what this is getting at is this illustrates that there could be a systematic difference other than the training manipulation between the group that received it and the group that did not. So we can't say for sure what caused the effect. It could be this pre-existing difference, or it could be the training. We don't know. One way to help minimize other systematic differences between groups, or also known as individual differences, is random assignment. So this means that we would have to select who receives the training and who does not receive the training completely at random. So this then allows us to assume that the groups are roughly equal on all other characteristics because everyone had an equal chance of receiving the training. Okay, now let's try it out. So we come across headlines like this all the time. Part of it is intentional, they need to get readers, and so the more attention grabbing it can be, the better for them. But here you can clearly see the author is implying that watching TV can cause death. This is from a real news article, and this news article is based on a real study. So let's review their methods to see whether this is causation or just correlation. So take a look at this summary of methods, especially the two sentences that are highlighted. Yes, correlation. They just asked participants how much time they were spending watching television, and then they built the categories based on how much time they were already spending watching TV. So there is no random assignment. So there could be pre-existing differences between the three categories that is associated with why they watch different levels of TV that actually could be causing them to be more likely to die from pulmonary embolism. For example, they could have health issues already that are associated with that makes it difficult for them to be mobile. And so when it's difficult to be mobile, there's less options for you to do beyond watching TV. So that could be the thing that is causing both situations. Another way to account for the systematic differences between experimental and control groups is to have everyone go through both conditions. So now there are no differences between the group because the groups are the same people. This approach does not apply well for AI ethics training example because once you've been trained, you can't undo the training, at least ethically. One example, from my work that might apply it better is that, we wanted to see if people's emotional state influenced how they responded on our personality test. Because you can be happy after you feel sad and vice versa, you could use a within subject design for this. So now our independent variable or cause is emotional state, and the dependent variable or effect is personality score. Now we are not comparing people to other people, we are comparing them against themselves. To do so, we need multiple observations on the effect to see if it changes. We could have all participants take the assessment 2 times. One time when they are happy and another time when they are sad, so that we can see a change in our cause from a happy time to a sad time. We can manipulate emotion by showing participants video clips known to elicit certain emotions. And that's exactly what my colleagues did in this project. Now we know that any difference on the personality test is not due to individual characteristics because the same exact people took it under both emotional conditions. Okay, but there are other potential causes we could rule out in both the training example and the emotional testing example. As these other potential causes are known as threats to internal validity. Both of our designs so far help us rule out individual differences as a potential alternative cause of the effect. There are other potential causes known as threats to internal validity. Internal validity is just the degree to which we can be confident the independent variable caused the dependent variable. And so it's a matter of removing as many alternative explanations as possible, other potential causes as possible. The threat to internal validity we have already taken care of is known as selection effects. This is when the process of assigning people to groups creates a difference that could have caused the outcome. So in our AI training example, remember when people just volunteered to take the training? That created a selection effect because volunteers could have just been more interested in the content of the training because they already knew a lot about it, or they already had previous experience with it. Random assignment helped us address that, and the within subject approach helped address that with our emotional personality testing example. And in the case of random assignment, there is still room for error. So we are assuming the groups are equal by operation of randomization. But in reality, there could still be pre-existing differences. One way to check this is to administer a pretest. So in our AI training example, we could have both groups take a pretest on the knowledge test for ethical AI use. Then we compare their scores before the training to make sure that they scored equally, to make sure they start out on equal playing fields. This helps minimize the possibility that there were pre-existing differences that are affecting the effect. So this starts to get into what is known as factorial designs, where you have a between group component and a within group component, because you have a pretest and a post-test, and you have two groups. Okay, cool. Now, in both experiments, we have people taking the outcome test twice. Wait, have you ever taken the same test twice? What happens if you take a test once and then take it a second time, the same exact test? You probably get better. In fact, you are likely to score differently the second time you take a test, even if you don't study in between the times you've taken it. This happens because you have already seen the questions and format of the test. You are more familiar with it. So in our between subject AI training design, we could use what's known as the Solomon 4-group design, where we have 2 experimental groups and 2 control groups. Only one of each receive a pretest. This allows us to directly compare groups with the pretest versus groups without to check for pretest effects. And so just to kind of walk through this graphical depiction of experiments, you might come across this pretty often. This is kind of a standard way to describe it. Each of the rows represents the groups, and each of the O's represents an observation or the time that you've administered the test. And then the X represents whether they receive the treatment or the training or whatever it is you're testing. So in this situation, we have this first group, they have a pre-test, they receive the training, they have a post-test. The second group has a pre-test, they don't receive the training, so they are a control group, and then they receive the post-test. The third group, no pre-test, training, post-test. The last group, another control group, no pre-test with only a post-test. And in our within subject design, we can address this by switching up the order. In other words, we would choose at random half of the sample to take the personality test while they are sad first, and half to take it while they are happy first. Then both groups switch and take it again in the condition that they haven't taken it in yet. This helps cancel out the potential impact of taking the test for the second time when, say, they are all sad. So this tactic is known as counterbalancing. Counterbalancing also helps address another threat known as maturation. This is just things that naturally occur with time that could influence the outcome. For example, over time, we always get older So our brains and bodies change. We could get wiser or more knowledgeable just with the passage of time. But what do we do in our between subject design with the ethical AI use? So maturation could be at play here. For example, let's say the training takes 5 weeks. Many things can change over 5 weeks. Your brain could develop a little more and allow you to understand AI better, for example, leading to better scores on the knowledge test. We can address this by keeping the timing the same for both the experimental and control groups. Because the groups are randomly assigned, we can assume they receive equal maturation rates on average. And so any differences between the group would still be most likely because of the training. Another thing we can do is add multiple pre-tests at different time points to capture any trends over time, and this will help us determine whether there are any maturation rates. What if in the ethical AI training example, the fact that people are receiving training indicates to them that you want them to perform better on the knowledge test? This added pressure alone could cause them to pay more attention and score higher than the control group who is not receiving any training. This is an example of demand characteristics, where the nature of the research procedure provides cues to participants that influence the way they behave on the outcome of interest. One thing we could do in this situation is to give the control group a different form of training to make sure that they have a similar experience to the experimental group. The idea is to just isolate the difference we believe constitutes our cause. So if the particular content of the training, if it's the content of the training that we believe is what is causing the change, we would only want to change the content of training across the groups. We would want the facilitator be the same if possible, the room, and so on. So building off that example, let's say the researcher administers the test after the training, and you are aware of which participants are in the control group and which are in the experimental group. So your awareness alone could lead you to interact with each group differently. For example, you might subconsciously smile more when you are interacting with the experimental group. Your behavior could change a little bit, your body language, and it could be enough to influence how they perform on the knowledge test. Maybe because you act a little bit happier, it motivates them a little bit more to score better on the knowledge test. So one thing you could do in this situation is have someone who is unaware of the design and administer the test. This is known as blinding. In other contexts, you hear about double-blind procedures, and this is where neither the experimenter or the participant knows which condition they are in. That's hard to do with a training because they are receiving the training. If you have the training actually cover other content on ethical AI use or make it similar enough, you could probably do that. But this is more common in things where they are testing the effects of medicine, and that's where they give people placebos, and they don't tell them whether they're getting a placebo or not.